Okay, we're going to have a look at a little bit of a momentum example question. The way that I've set this up is part one is relatively easy, part two is a little bit tougher, requiring some use of simultaneous equations, but neither of them are particularly challenging, I don't think. I guess we'll see. I probably shouldn't say that, because if I say they're easy and you find them hard, it can be disheartening. So they are exactly as easy as they are. Right, so I've drawn a surface. I've drawn my 3 kilogram ball, which is moving right to left. Got to read the question carefully. It has a mass of 3 kilograms. I also have a stationary ball of mass 1.2 kilograms. That's a little bit untidy. And it's moving right to left at 2.4 meters per second. So that's my initial situation. The ball from the right is going to come in and hit the ball on the left, the 1.2 kilogram ball, and in part one it remains stationary. In other words, the 3 kilogram ball stops and the 1.2 kilogram ball moves off. Now, we just intuitively we might think if a larger ball hits a smaller ball and a larger ball stops, that the small ball might move off quite fast. So intuitively we think possibly an answer higher than 2.4 meters per second. So let's just test our intuition and see. So overall momentum before the collision, because remember momentum is conserved, so before the collision, P overall total equals mass of ball 1 times velocity of ball 1 plus mass of ball 2 times velocity of ball 2. P equals mv. Because I mentioned the 3 kilogram ball first, I'm going to call that ball 1. So equals 3, the mass of the 3 kilogram ball, times its velocity, 2.4 meters per second, plus 1.2, the mass of the second ball, times its velocity, which is just 0, which makes that term go to 0. So the overall momentum is 7.2 kilogram meters per second. Kilogram meters per second is the unit of momentum. There's not a simpler unit for that. Okay, so that's it before the collision. Now we know that after the collision the overall momentum is going to be the same. So we'll set up the situation after. P equals still m1v1. We could add m1v1 B for before and A for after, but it gets fairly complicated fairly quickly. So it better maybe just to keep our wits about us. So after we've been told that the 3 kilogram ball has a massive velocity of 0, it's stopped, and the 1.2 kilogram ball has a mass of V2, which we don't yet know what that is. We haven't figured it out. But what we do know is that P overall is going to be 7.2 because it's the same as before. The momentum is conserved overall. So with that we know that 7.2 equals 3 times 0 is just 0, so we can ignore that term. 1.2 times V2. If we rearrange that a little bit, we'll find that V2 equals 6 meters per second. If we do the maths. And that means that, yes, our intuition was right. The 3 kilogram ball was moving at 2.4 meters per second. The 1.2 kilogram ball moves off at 6 meters per second. Now what we haven't done is be careful about our direction, but right to left we put it in as a positive, so right to left is going to continue to be our positive direction. So that means it moves off at 6 right to left, in other words toward the left of the page in our diagram. Okay, so that was the relatively easy one where lots of stuff went to 0, so we didn't have to deal with slightly more complicated things. Let's have another go. Same diagram, so I won't redraw the diagram, but in this case we're told that the 3 kilogram ball, instead of stopping, ends up with a velocity of negative 0.2 meters per second. Now remember, we've picked right to left as our positive, so negative 0.2 means it's moving off left to right. So the ball has bounced and gone back in the direction that it came from. So for before, the situation's exactly as it was above. So we don't even need to rewrite that equation. The situation before is the 3 kilogram ball is doing 2.4, the 1.2 kilogram ball is stationary. The overall momentum before the collision hasn't changed. It's 7.2 kilogram meters per second. After the collision, in this new situation, after P equals M1 V1 plus M2 V2 equals 3 kilogram ball now is minus 0.2 meters per second, and 1.2 kilogram ball is now still V2 unknown, but it will be a different V2 from what we had before. So with same kind of thing. So actually we don't need simultaneous equations in this one. It's not quite as tricky as I promised it was going to be. So 7.2, because the momentum is conserved. 3 times minus 0.2 is minus 0.6, I think, plus 1.2 V2. And we can rearrange that, and we end up with, if we rearrange and calculate V2, if we calculate that out, we actually get 7.8 divided by 1.2 is 6.5 meters per second, which is just very slightly faster and in the same direction. So it heads off to the left again, but a little bit faster. And that makes sense because we've given a little bit of momentum in the negative direction, the left to right direction, to the 3 kilogram ball. So for momentum overall to be conserved, we have to give a little bit more momentum in the other direction to the 1.2 kilogram ball. So that's internally consistent.